Compound interest, what is it? Unlike simple interest, okay, compound interest is very different than simple interest, okay? Interest is earned on both the principal and the accumulated interest. So you kind of earn interest on the interest you've already accumulated before. Most financial institutions, banks, credit cards, credit unions, they charge pay or charge compound interest. Compounding periods, this is a different color here because I need you to really understand this. Compounding periods refer to the amount of times the interest is calculated in a year. When you see the keyword compound, you may not use simple interest formulas. Please do not go back to simple interest. If you see the word compounded anywhere, you're in compound interest territory. Since you're earning interest on previous interest, it creates what we call a snowball effect. Okay? Your investment will essentially grow faster, and similarly, your debt will cost you more interest. Okay? You grow faster, but at the end of the day, when you owe, it's also going to cost you more interest. The relationship between time and money is exponential. So, on your study sheet, next to compound interest, I need you to have time and money, and it's not going to be linear. It's going to go like this. Okay? So it's exponential. There's your graph. But listen carefully to this part. It doesn't mean that compound interest is always going to beat simple interest. It doesn't necessarily mean that. It has to do with interest and time. But if all else is the same, compound interest is usually the winner. This would be, this one right here, this would be simple interest. Simple interest would be a straight line. So you can tell that there may be a time where the compound is underperforming, but then it meets it and exceeds it under compound interest scenarios, okay? So this is the formula, the very, very simple formula. I don't want you to have that on your study sheet. I don't want you to have this one on your study sheet. I want you to have the boxed in version right here. This one. Study sheet. And have this entire chunk in there. Okay, so it looks, at first looks the same, but what do you notice? That there's an exponent here. Okay, and here it tells you what everything represents. A is still the future values, how much money you will have in the future or how much you are wanting to have. Principal is obviously the initial investment. R is the interest rate. N is the compounding periods. This is new. And T is still time in years. And if you need to know compounding periods, how often interest is calculated, annually it would be 1 time a year. By the way, this right here is N. Okay? So if compounding is annually, then N is equal to 1. If it's monthly, N is equal to 12, and so forth. So the word tells you what the number is going to be that goes with it. Okay? Okay, weekly 52. So let's do some math here. I'll give you an example, and then you can try that out. Okay? 17. Greg is 15 years old and inherited $150,000. Not bad. Okay. From his grandmother, and would like to invest it so he can use the money to purchase a house when he turns 25. So 15 to 25, right? He has the following conditions. So option A, 4.5% rate compounded monthly. That right there tells you that N is equal to 12. Option 2, 4.5% Compounded semi-annually. What is that? N is equal to 2. Semi-monthly is twice a month, so it's 24 times a year. Semi-annually, it's twice a year. There we go. Calculate the future value of each option. It's asking you to figure out what A is. Okay? So I have a line in between right here. So let's do option 1. You start with the formula. 1 plus rate divided by compounding periods to the power of compounding periods times your time. So it looks scary, but it's actually very doable. Principal. The principal is 150,000 in this case. And that's 1 plus, the interest rate is 4.5%. You got to make sure you divide that by 100. Okay? And then N for option 1 is 12. So you put 12 in here. And then you're going to go 12, so the N shows up in the denominator here, and then again in the exponent up there. And what's my time? 10, yes. So I encourage you to do this because quite often the province gives you the starting age and the end age. So you just quickly do a 10-year. That's where you get the 10 from. So your time is 10 years, so you multiply that by 10. And then we clean it up. So watch how I do it. You may do it differently as long as you're careful. I figure out what's inside the bracket. So, but in reverse, watch how I do this. 0.045 divided by 12. So you gotta divide first inside the bracket. Then you go plus 1, right? You add the 1 to it, and you get this inside the bracket. So it's 1.00375. You don't have to write down all the decimals if you don't want to. Just go dot, dot, dot. And then 12 times 10 is 120. This looks like an exponential function, right? Right here. B is greater than 1, so obviously my money is going to go up. So this is where I take this to the power of 120. So it's on my calculator. I just go hat. I press the hat button, and mine does that, and I go 120. I just type in 120 there, and you get that. So it's 150,000 times 1.5669 and something, right? No more exponent. And then the last step is to take that and multiply it by 150,000. And there you have it. After 10 years, that 150,000 will have turned into 235,000. That's why, especially when you're young, time is on your side. Time is what makes money grow exponentially. Okay, so that's that. Can you give this a try for the semi-annually? The N is equal to 2. I hope you're gonna be able to do that. Try it and then just look up if you're once you're done. I will just do it silently. You do your own thing. Which one made more money? Option A. Why do you think that is? What's the only thing that changed between these two? The compounding periods, right? More compounding. Everything else is the same. If everything else is the same, you want the more compounding every time. Okay? If it's hourly, daily, like daily would be even better than monthly, right? So anything that has where n is bigger, that's the option that you're going to want to go with. Okay? Am I saying that? No, not yet. B. B is asking calculate the total interest earned. This is an important skill. For both of them, how much did you earn in interest? I would like you to use this formula. This one has been with us this whole time. Sorry. I'm trying to think what I gave you. I think this is the one. Always remember that the final amount that you're getting is always what you've invested plus any interest that you've earned. Okay? Let me just scroll down a little bit. That's always true. This concept is always true. So basically in this case, from this we can derive that to find the interest, what are we going to do? P comes over to the other side, subtracting, right? You take the final amount and you subtract P from it. Same here. This formula is maybe something worth adding to your study sheet, but that's how we find our interest. We take what we have at the end and we subtract what we started with. That's the basic principle of investing. So we started with 150,000. So here we made $85,000 and 48 and 92 cents. Okay. Interest here and over here. It's going to be a little less. $84,076 and 48 cents. What's the rate of return for each option? We all know that the rate of return for investment on option 1 is going to be higher, right? But if I ever asked you to calculate it, in this case you have everything you need. You earned 85,000 and you put in 150,000. Multiply that by 100. I know that you're, I'm not calculating this with you. So they're almost the same, but slightly more with option 1. We earned more interest with option 1. Okay. And if you like highlighting, where did I get my numbers from? This interest is here, right? I'm just going to do it on the one side. D. What can you conclude about compounding periods and the effect on the future value? Okay. All else equal, meaning the time is the same, the interest rate is the same. Okay. The more compounding periods, the better. Interest is calculated more often. Interest is calculated more often. That's why it grows faster. I have to do rule of 72 and then one more. Say, it's going to be a little tight. If I run out of time with that other example, you're going to have to watch a 5-minute video over the weekend because I want to get it done. 18, and do any homework that I assigned today. Estimation tool. So the rule of 72, add to your study sheet. This is on page 18. The rule of 72 has two versions, okay? They both have the 72 in them. And this is an estimation tool. I believe Albert Einstein came up with this. But it's a very cool estimation tool. Okay. So if you want to know how many, the doubling time, okay, what is it's basically the rule of 72 tells us how long it would take for an investment to double. Okay. So this essentially, if you want to put this in bracket, it gives you the doubling time. This one in particular, the first version right here, where you're trying to find the time in years. And you do not convert your percentage to decimal. That is key. You keep it as is. I do have it right there. This is essentially the doubling time. But it doesn't hurt to write it one more time. If you want to know the interest rate required to double your money at a certain time, so let's say I want to double my money in 10 years from now, you would go 72 divided by 10, and then you get the interest rate you would need to make that happen. Okay, so these are very much related. This is the most popular one out of all to figure out your doubling time. So how does that work? Do you see money anywhere in here? Dollar amounts? No, it has nothing to do with that. The doubling time is independent of that. So here we go. Mr. D would like to double his $250,000 secret stash in 5 years to retire early. What interest rate would he need? Answer using the rule of 72. You have to use the rule of 72 if the question ever mentions that. I want the interest rate, so I'm going to use this one. 72 divided by time. So I would go 72 divided by, I want to double my money in 5 years, right? So you just go 72 divided by 5, that's 14.4% interest rate. Okay? Needed. So I need to go find an investment or make a portfolio that gives me on average 14.4% annually. Okay? That's how you work it that way. Backside of this, we're not going to use the compound interest formula to verify this. It works. Trust me, it works. It's been around for decades. It works. Okay. 19. How else are we using the rule of 72? 19. Heiko would like to invest $6,000 at a rate of 2.35% compounded weekly. Use the rule of 72 to estimate how long it would take for his investment to double. Explain your answer. Okay, so what we would do here is time. We want to know the time to double. You take 72 divided by 2.35%. It would take, at that interest rate, it would take 30.64 years. So if you had $1 invested, it would take you 30.64 years to get $2. If you put $6,000 in, it would take you 30.64 years to get 12,000. You know what I mean? Like, the amount of money doesn't matter. It's that the fact that it will take this much to double whatever you put in. Okay, so that's the cool part here. So let's say, listen to this part. I don't want you to round, but let's say approximately 30 years, correct? Doubling time. So, time and money. How much do we have at the very beginning? 6,000. 30 years go by, how much will we have? 12, right? Does this look like something we've done before? Doubling time. 60. You'll have twice of what you had before, 24,000. Another 30 years go by. You double what you had before again, so you have 48,000. So you can quickly estimate, right, how much money will I have in like 50, 60 years, right? Like you do round numbers just to estimate. So sometimes I will actually ask you to use the rule of 72 to first come up with your doubling time and then maybe figure out how long it will take you to have $24,000. How long will it take you to have $24,000? 60 years under these circumstances, okay? We're not going to verify. We're just going to leave it at that. So I'm going to stop here. Page 20, just one question. I'm going to ask you to watch it, okay? So watch video. And there's compound interest worksheets that come with it. So I'm going to go page 23 to 26. So 23 to 26, there is some rule of 72 back there. I'll show you real quick. So I'm skipping these tables for now. I don't need you to figure that out just now. So start on 23 here. It's just compounding. And then when it gets to 25, 26 that is, that's when rule of 72 starts appearing, okay? So you need to be comfortable with that. Look at the key, make sure you understand what's happening, okay? What's in store for you next week? Next week is when I start with something called TVM solver, okay? So we actually use our calculator to figure out, we use this screen right here to figure out how much you need to put away every month to have $1 million when you retire, things like that, okay? Or let's say you want to have $30,000 by the time you turn 30 to buy your first house, how much you need to put away. If you want to buy a car at this interest rate over 5 years, what will your monthly payments be? All of those things, this thing is awesome for that. You can do a lot of what ifs. What if my parents give me $20,000 when I turn 18? What if I put that into a savings account at 7% over 40 years? What happens to that money? What if I turn 50, I start adding a bit of money to it every month? So all those what ifs.